This is a talk about LCD codes. Everybody can hear me all right?
Yeah. Yep.
Yeah. Okay, good. Okay, which are linear with complementary dual is the LCD codes. I know it's not a very nice acronym, but there you go. Which are codes, error-correcting codes in which the code and its dual, C-perp, intersect in 0. Now, the talk is going to be about work I've done with Washila Fish and Eric Mwambeni at UWC, Bernardo Rodriguez at UKZN, Tom McDonough and Baz Mavron in Aberystwyth in Wales. I gave the talk in Westville a couple of weeks ago, but it was not a video talk, so it was designed for putting it on a screen and for me to be able to write a few things on the board, which I can't do here. No. Okay, let me see if I can get this right. Okay, so here it is. So, LCD codes are codes that C intersection C perp is 0. The term was introduced by Massey in 1992, and the reason he introduced the term was because these sorts of codes have got a lot of applications: data storage, communication systems, consumer electronics, and more recently, cryptography. I've written out whole C. This is a term Ed Asmus and I introduced in our book in the 90s, and it was really for designs and a projected plane, because the hull, we wanted the big hull, which is almost as big as the code, possible, but here you've got the converse situation, you've got a small one. The term hull is something to do with topology. I don't know, it was Ed's idea. But so here, if you've got the hull 0, then it's equivalent to the space being a direct sum of C and C perp. This is okay. And always I'm talking about codes over finite fields. These are finite spaces. So what was the interest in these things? In his paper, which is a very nice little paper, very easy to read, from 92, I guess I could probably, well, if anybody wants the reference, okay, I'll have it going there, but this could be a disaster. There it is down there, Massey, in discrete math, it's easy enough to get, 1992. Okay, now I'm going to attempt to go back. This is that mouse, okay. Scroll, I think, yeah. No. Okay. Okay. So it's a nice paper. What he shows is that it facilitates decoding, nearest neighbor decoding, in that all you need to do is to express all the words in the whole space in terms of their direct product, what their part that's in C and their part that's in C perp. And then, and this is the tough bit of it, in fact it's not so easy, is that you need to find the nearest possible word in C to a word, any word in C perp. For some cases, this works quite nicely, and I'll show you, but this is the tricky bit of this. So if you have a question about that, that's where the big question is. So I'll show you how that works. KRA, I went west, you problem? Yeah. In K, down here, in this KRA, this is Key and Rodriguez, we first discovered this way of getting codes that you can split easily from undirected graphs. That paper is not quite published, but it's almost, it's waiting to go. It's online first. So these things come from graphs. There's been a lot of discussions on sort of work on codes related to graphs, and I'm talking about codes from the adjacency matrix. The other ones are not quite as well; they're easier to work with, but the adjacency ones are sort of tough. They're all different for different graphs. So you take an adjacency matrix for a graph, and I'm writing CP of A to be the span over a finite field, characteristic P, a finite field, or a prime field, you might as well do that. And then we also look at A plus I. This is the identity matrix, so you just basically got ones down the diagonal of A. And that, as a graph, that's called the reflexive graph. And we look at the row span of that. And this is just a notation. If I call C the code from here, RC reflexive C is written like that. Okay, so this is just a bit of a notation just to explain what's going on here. So A is the matrix, and Rx is the row of A corresponding to a vertex in V. So it's a 0 when you've got a vertex not adjacent to A and 1 otherwise. Sx is the same thing for A plus I, so it looks like that, but it's got a 1 on X, whereas this one didn't. And so again with that, Vx, this is a notation from my book Z. I found it quite useful. Some people like it, some don't. But anyway, this is V to the, for any subset of vertices, V to the S means the characteristic vector of S. So it has 1 in S positions and 0 elsewhere. This one, slightly abusive notation, that should really have curly brackets around the X, but omitting those for simplicity, Vx is then just this Sx minus Rx over any fields. So anyway, the whole space, F to the V, is the sum of these two, but normally not a direct sum. Okay. So just from simply looking at A and A plus I, C perp is always in RC, and there's the reason for it. If I take something in C perp, X in C perp, then XA is 0 by definition, means XA plus I is X, and voila, there's X is in RC. For the second part of it, if A squared is minus A, that means 0 is A squared plus A, is A times A plus I, and so therefore RC is in C perp, or vice versa, also C is in RC perp, but that's... so if R is equal to, RC is equal to C perp, then it's LCD, the whole is 0. And that is because f of eta is the sum of these two, is now C plus RC, is now C plus C perp, and therefore its perp, its dual is 0, because the dual of the full space is 0, so that means C intersection C perp is 0. So it's a direct sum, and that's what we like here. So this is just a, oops, okay. This is a, Bernardo and I wanted to just have a nice term for this, so we call these reflexive LCDs, RLCD. I'm not married to this term, but it's just useful. It's distinct from just plain LCD, because you can have codes from graphs that are LCD and not reflexive. In other words, a C perp, that thing is not RC. So there are plenty of those around, and we've all found those in the past as well. I've ignored those. I didn't know they were important, but the coding theorists told me they liked it, so, and I see they are nice, yeah. So how do you express a word? So this is any vector in f of v. And I want to know how to express it as a sum of vectors. I've got an RLCD code, as it says up there, and so I know RC is C-perp, and therefore I know that the space is a direct sum. So I would like to, and in general, it's not an easy thing to do, something's a direct sum. How are you going to find the unique, the breakdown of any word? So here, so I'm writing this. What this means is the W of x is the coordinates of x at the points at x. Is the coordinate of W at x, and then v to the x is it'll v to the x as usual. So this is the word with support wx, support of w. And now you've got this from before. So w, so now I'm going to write for v to the x, this thing here, sx minus rx. And there you have a splitting, whoops, something's happening. There you have a splitting into the two bits. This is the bit in C, and this is the bit in C-perp. So it's as easy as pie to do that. That comes for free if you've got RLCD. Normally for LCD, it doesn't come for free, and you've got to work hard to figure out how to do it. But this sort of way, I think it works for codes from designs if you can do it as well. This sort of idea of summing vectors like this. It's not. It has some structure in the code words. It's possible that this will always come out quite nicely. But anyway, so certainly for RLCD graphs, you got this. If W happens to be in C and it is its support, then W is just the support, so it's just X in C. So it's just that sum. The sum of the WX with X in the support. In particular, if it's a binary code, then that's just 1. So W is just the word with support. Well, of course, then that's a plus if it's a binary. With support, it's just some of the rows that give it support. And it also tells you, more importantly, that this thing is 0. And like the same thing holds for RC, there's no difference between RC and C as regards codes, they're dual to one another. So you get the same thing, that it's the sum of the SX, and that likewise the sum of the R's is 0. So that's quite neat. Okay. So Massey had a little way how to. He spoke of how to split he had a mapping, splitting the word and then showing the decoding procedure. It says up here. It's not a good mouse one. Okay. So as I said, it only requires this. You need the nearest neighbor in C to any given vector in C-perp. So in the RLCD case, it works as follows. You have, and this is the tricky bit, this map here. Map from RC to C, such that U in RC maps to one of the closest neighbors, V in C. Now, if the errors are at most the error correcting possibility of the code, so D minus the minimum weight minus 1 over 2, integral part of that, then this will be unique. But otherwise, this won't be unique. So that's always a problem with nearest neighbor decoding. So you've got to set up this map. And that's once you've got that map, if you can do it and come to some decision about it, then another one, map phi tilde, taking the full space to C, such that when a word W arrives, you split it into its bits. This is the first bit, and that's the second bit. And then for the second bit, for the bit that's in C-perp, you take phi of it, and then you decode as this. So you assume that's going to be the closest word to the one sent. This is now a word in C like that, because that phi maps into C. I can show you a little example. So this is So suppose I've got a minimum weight D, so there's the T there. Sorry, it's just a break for water. Now, just looking at a set, just for some examples here. If you take, if you look at any set sum of rows, they are V to J. If it's over a set of J, Si, I, and J, then it's equal to V to the J plus the sum of rows from A. And if J is at most T, then, which is the error correcting possibility of the code, then phi, you can define your map phi easily just to be the sum of the Ri's, so over J. So, for example, if W is Vj comes in, which has got weight less than or equal to T, then you must decode it as, according to this tilde thing, the sum of those, the sum of the R's, plus phi of those, which is 0, and that is correct because 0 is the closest word to that in the code. You can do a bit more on that. It's, I haven't figured it out. We only started working on this a couple of weeks ago. We were rather looking for graphs with RLCD codes. So that's, as I said, that's work in progress. Various classes of graphs. We looked at various classes, so what we looked at, Bernardo and I looked at strongly regular and uniform subset graphs. More recently, with Washila and Eric, we sent a paper about Hamming graphs, and Bernardo and I are currently working on Pizer graphs, which I'll tell you are strongly regular with the same parameters as Paley graphs. Paley graphs are strongly regular graphs, are the famous ones because they're binary codes with the quadratic residue codes, which have got a lot of been used for ages and ages, and you can say quite a lot about them. So I'll just talk a little bit about the Pizer ones. But first of all, it says strongly regular. I'm just rattling on here. I don't know if anybody wants any questions or anything or wants me to slow down. So I can hear stuff. So just shout, I suppose. Okay? Okay. So this is the definition of a strongly regular graph. It's we're excluding complete null. So these are parameters nk, lambda. First of all, you say regular of x, k. And if you've got two adjacent vertices, they're together, both are together adjacent to lambda vertices, and any two non-adjacent vertices are together adjacent to mu vertices. You get a 2 design if mu happens to be lambda, but we don't particularly want that, and especially not for RLCD codes, as you'll see from the next result. So that's lambda if they're adjacent, mu if they're not. It's just the thing to remember here. I think this is pretty standard, amazingly enough. Everybody uses that terminology. And so this KRA is this paper with Bernardo from something, applicable algebra, etc. What does that mean? Okay, anyway. Somebody pinged. Okay, so if you've got a strongly regular graph with an adjacency matrix, P prime, okay, C and RC, then C is RC, in other words, it's RLCD. If and only if, very simple conditions here, k is congruent to 0, lambda is congruent to -1, and mu is congruent to 0. So just looking at those two, obviously the ones where we're designed where lambda is mu are right out of the question. You're not going anywhere near that. The eigenvalue, well, we don't really need this. The ones I'm going to talk about have clearly got dimensions we can work out. So this is just, well, I don't really need to go through this. This is just to show with those conditions that, well, I suppose we can talk about it a little bit. So CPEP's already in RC, so for the reverse inclusion we need that the inner product Rx and Sy is common to 0 mod P for all X and Y in V. So first of all you check out Rx and Sx, that's okay, so you should that be common to 0 mod P. If they're adjacent, then Rx, Sy, the inner product is 1 plus lambda, and if they're not adjacent, it's mu. So either way, those conditions come in, and you get, since we got the first bit, and you get C as RC perp. So that was a particularly simple thing to work out. Okay. So in the Bernardo paper, we looked at some others, triangular graphs and things, but nice ones are the Paley graphs. So the Paley graphs, of course, I'm not going to work on them too much because they've been studied by a lot of people, but the Paley graphs are famous in that term. So any two, the space, the vertices are the set of all numbers in prime field, FQ, prime power field, FQ. X and Y are adjacent if X minus Y is a non-zero square in FQ. So if you've got FQs, if omega is a spanning primitive element, then X is adjacent to Y, if and only if X minus Y is in the space, the group generated by omega squared. These have been around for ages, and as I said, they give the quadratic residue codes. They're self-complementary, that means they're isomorphic to their complement, and strongly regular, and these are the parameters. And going back to what we just proved about when are they RLCD, for P is 2, you just need Q congruent to 1 mod 8. The Q's always odd, by the way, obviously, the Q's odd. Or, if you want to do some other prime, P odd, Q must be congruent to 1 mod P. And the dimension is a half Q minus 1, and the other guy, the RC is a half Q plus 1 power. This is a Brower and Fun IL, I think. I don't have the paper, but it's not hard to get this anyway. 92, yeah. So those are the parameters of the Paley graph. Stay clear of them because a lot of people have studied them. It's the curious thing about the Paley graph is hard to get the minimum weight. There's something called a square root bound. Let me just go back here. If Q is a prime, then there's a square root bound to the minimum weight at least the square root of Q. So there's very little. It's curiously hard to find the minimum weight of these codes. And there's certainly no formula for them all. So this is recent work, as I said, from with Bernardo, and it's these pi-z graphs that he found, which seem rather nice, and they're rather like the Paley graphs. Let me just give you to go down to pi-z. It's Wojciech, I think is the name, Wojciech pi-z. So that's General Algebra, so 2001. Okay, right, now, back again. So that's easy enough to get. It's a very nice paper. I'm just looking for the paper. This is it, yes. Okay, so this is, it's a kind of similar definition. Again, and here, again, it's going to be Q is a bit, Q is P to the T, 2T, it's got to be an even power of T, P to the T, even prime power. Omega is a primitive root, and you're taking this, Okay, so this is omega to the 4. This is the group generated by omega to 4. 4 is okay. It divides Q minus 1. You can check that out. And you also take with this, you said omega times that. So that's 2 times that in size, or you can look at it like that. And then you say they're adjacent if and only if x minus y is in M. So either x minus y is a power of omega to a power of omega to the 4, or it's omega times a power of omega to the 4. And it turns out, implies it showed this, that this graph is self-complementary symmetric graph, strongly regular with parameters exactly the same as the Paley graphs. So Bernardo and the automorphism group is particularly nice and useful for these pi-Z1s. The self-complementary tells you, I won't go through this in general, but the you've got well, this, don't worry about this. Is just sometimes you can get further automorphisms for small values of Q, and but otherwise you've got translations. It's like the affine group working on Q basically. You've got translations and these other two maps, gamma and delta, which are a little bit pesky, but anyway, they're reasonable to work on. And when p to the t is common to 1.4, you actually get another one, which is not much use. But the important thing is that A is a rank 3 primitive permutation group. So once you take a stabilizer of 1 point, you've just got 2 orbits. And that's due to its self-complementary nature. So that's useful in proving things about the codes. Okay. So we looked at binary codes. So the binary is always okay for these ones. So that's the code. Those are the parameters of the code. This means the length. That's the dimension. And that's the minimum weight, the mystery item D, which you don't know anything about. And then likewise here, that's because these two must add up to Q, and dperf. And that's also a mystery item. So we get a little bound for this. It's not a very good bound. It's perfect. I think it works in the very bottom case, but it's about a counting bound because of words. How can you can get counting bounds for a minimum weight if you know words in the dual, and we do know words. We can get words in the dual quite nicely. It's rather like some of the Paley graphs. Now, an ex-student of mine, Giraffa Limbo-Pasiriporn, actually in her thesis, she never published this stuff. She looked at Q as square for the Paley graphs, and she found words of weight the square root of Q plus 1, and showed that with the minimum weight of R of the reflexive graph, which she didn't use this term RLCD because we haven't spoken about it yet, but this is the C-perp, is the minimum weight of that is with Q, and words of the form with support of the field. Yes, the field F, the smaller field FQ, F root Q. Oh dear. Sorry. Okay. So we sort of achieved nice arguments in that thesis. If you can get on with it, it's pretty good. I wish you'd publish the stuff, but I don't know. Unfortunate students to publish things, but anyway. So she'd gone back to Thailand. But Bernardo and I certainly got ideas from her thesis, and so we looked at the Piezo graphs, and they always got the nice thing is they always got a square up there, so that's good. So what this proposition shows is just that since it's propositional, with definition again, calling C0 the subject spanned by omega to the 4, then if you have, okay, F is, so taking F for the little field, I think I usually use K for the big one, yeah. Okay, so it's a quadratic extension of this thing. We're going to use that, and that's useful. So what we found was that words with support YF for any Y that's not in M. So basically, say, for example, omega squared isn't in M, or omega to the cube. But if you've got a multiple of omega to the 4, or multiple of omega times omega to the 4, then they'll be in M. So, but these are just as useful to work with as the other case. There are some other cases where you actually have the word F, but not for this particular one. So, and I think I won't go totally through how this goes. It looks too awesome, but just to sort of outline what we did, and basically we used the fact that that K is a quadratic extension of F, so that therefore the elements of K, which are your vertices, can be written as A omega plus B, where M, B, and F. Now, this is useful, and it's not always useful, but it's useful in this context. So this is F, this little field here, it's spanned by omega to the pt plus 1. And so writing this M as this number here, which is an integer, just by the incongruences there. So we're taking C0, which was this C1, yeah. C0, C1, C2, C4. These are the baddies. This is M across here, these two, C0 union C1. C1 is just omega times C0. So C0 is all the multiples of omega to the 4. So I've divided them out into F, and then a bunch of M minus 1 of this form here. So these things are kind of linear independent. F, the field times some element of that form, A plus, where A and B are not 0. So you, and they're all distinct and independent of one another. And likewise for that one. So you can sort of divide out the elements according to your, to the extension. So there, and each of the CI are partitioned into n disjoint sets of size p to the t minus 1, that's these pieces, consisting of all the multiples of an element of CI by elements of F. Okay, so now, so I'm trying to prove that Y times F is in C per RC. So we can, so what does it look like? We can assume it looks like the form omega plus some B in F, not 0. Yeah, B is not 0. I should have said that really, because if it was 0, it would be in here. But so we can write it like that. M, of course, is closed under multiplication by F. By the F cross, and so we can. It's quite easy to see that you can write Y like that. So what we want to do is take the word with support of Y times F. And that's what this is. Yeah, remember we're talking binary here. So what we need to do to show that that is in C perp is to show that this word is equal to the sum of the S rows for X in the set W plus B, that's Y, times F. That was what we got out of our description of these RLCD codes. So we need to show that W has got this sum, has got support W plus BF. And that, what we do is we just look at the various U in K. K is our is a set of vertices, and consider the various cases of U. They kind of turn out to be rather similar. It might look a bit tedious, but it's not so bad. Actually, it all starts rolling along quite nicely, and it's a useful result. So I'm going on to the attack. So basically, now at this point, I would have drawn a little picture and put all the first set of rows, the first set of vertices I'll take to be the elements of W plus BF, and then along for the rows, they'll be labeled similarly for the words, for the vectors in W plus B times F, and have a look to see when you get one of these guys in here. So I'm trying to determine that this word, just its support is simply that. So this is taking the stuff in the beginning. If you take U as 0, use in S0, but not in the word SC plus omega plus B for any C not 0. So and similarly, if you take one of these, you'll find it's in its own. Because it's an S thing, so it's in there, but not in any of the others. So your first bit of the matrix is just the identity. So your first little square is just ones down the diagonal and zeros elsewhere. So it's a good start, but there's a lot more work to be done. And so I'm not going to go through it all, but so now I think the next easiest case is taking something from F, from the non-zero element from the smaller field F, and saying how many, I'll just look at this one and then we won't do any of the others, and say, so these are the rows that we're looking at, the SC omega plus B. So I'm supposing, say, we're using S0. Do I care about that? Yes. Okay. So you've got S0 across the top always, and A is in it. Now here, if it's in it, then you know this thing A must be this element C omega plus B plus some Y. This is not the same Y as before. For some Y in M. I should have changed that notation really. But anyway, so then just sort of arguing where Y can be. So this is now you look at M. Let me just go back. Here's M. So this is the set of elements in M. Those and then omega times those. Okay. So now you can just argue to see how which elements of M it can be in, what this Y can be. So I've argued here, it's just algebra, and we get the number of possibilities is 2 plus 2m minus 1, and then because of our congruence for m, we get that's even, and so we get the 2 is coming from is I think you get 1 from 0, but anyway it works out because it's binary, so you get WA is 0. Now this sounds sort of tedious, but in fact it's not so bad. It's reasonably easy to all the arguments are all rather similar, and so go through the cases, and there's only five cases I think, yeah, to look at, just looking at elements in the various different positions. And so finally you find the only place where you get ones is that first set. So this word is now in the dual. Okay, so I'm going to do something here it's sort of a little standard sort of counting argument to using words in the dual to attempt to get a bound on the minimum weight of the words in the code. And this particular, so I want to try and use these words with support a multiple of f to do that for these codes. So here, this first thing is pretty elementary. It's a quadratic extension, and these are just cosets really. These vectors, they only meet, and this I've used E here because it's true for any LD, but you can use any for any subfield. But in our case, our E is going to be fp to the t, I think. Yes, fp to the t. So Q being a quadratic extension in that case. So then these guys don't intersect, or they're equal. And similarly for the cosets like that, they intersect or they're equal. So, and in particular for f is f to p to the t. So if you now, that's a really easy thing to use for a projective plane, if you like, which is exactly that in its definition. So now we can get a bound on the minimum weight of C, and it doesn't look very wonderful, but it's better than nothing. I mean, we can get plenty of small words to see, but we can't do much better than this. And I would like to have a board here to draw some pictures, but basically, well, let's see, maybe we can get something. So you take a word in C, and with support size S, and let's suppose the thing is transitive, so we can put 0 in S. So I want to know that the word with support UF, where F is in RIC for appropriate choice of U is determined. Okay, so for example, U not in any U that's not in M. Well, looking at the stabilizer G0, it's got 2 orbits because it's rank 3, and they're both of length Q minus 1 over 2. So one of the orbits are the elements of F, the non-zero elements of F that are adjacent to 0, i.e. M, and the others are those that are not adjacent. So that's your 2 orbits, each of length Q minus 1 over 2, I guess, yes. Now, you've got mappings gamma and delta that map these things. The sets U, F will be mapped onto sets of the same form. They have to be within one or the other orbit. And since it's transitive on elements in each orbit, sets of this form don't intersect. And the number of sets are, now you just do a count, Q minus 1 over 2, you ought to divide by P to T minus 1 because each of these things has got that number of elements, and you get that. That must be, these things meet S again at least once, and they don't interact at all. They've got to be different. They don't intersect except at 0. So that means there must be at least that number of elements in the set S. Well, that's okay, but I said something better than that. And so you get S is at least 1, that's the 0 plus this. But since the J vector is in RC perp, since Q minus 1 over 2 is even, you can't have a constant vector, well, I mean, it's binary, so that's irrelevant. You can't have one of odd length. So that means you can stick on another 1 to that and get that for your bound. So it gives some, it's some sort of bounds. Just to show you some tables of computation. Oh, well, no, this is not computation. This is this is the small words that Bernardo and I found in the codes. So for this is if it's gone into 3 mod 4, you get them over 4 F cross union omega F cross. So that's of size whatever it says up there, 2 root q minus 1, and this one is of size root q. Sorry, root q minus, yeah, root q. This is the whole F, yeah. I managed to get this with P to the T is going to 1 mod 4. I haven't really got any idea about that one. This guy's okay, but it's hard to get that. So that one, I haven't got handled that one. But it's they're not many. Mostly they're the next one up after the small 7. I think is rather large. So you probably can ask magma. So this is from magma. The various codes. So this is pure magma. Okay. So this is what magma says the minimum weight is for C and C perp, and these are binary ones, but in fact the others don't look very different when they work, when they say they're full space. So these, at this point, I couldn't get the minimum weight, but I've got that little P to the T bound thing gives 12, and then the fact that you can make vectors of weight 36, that's 2 times 18, gives you that. And this one, this is the size of the field, 19. I believe this is the minimum weight, but I mean, one can't sweat it. So this is the size of the field. You see, again, this is behaving like the Paley graphs and what Giraffe proved for the Paley graphs when Q is a square. That you get the words in the field are precisely the minimum weight vectors of RC. So it would be nice to prove that, but we haven't done that yet. So most of the there's also something called generalized Pfizer graphs that some student of Chris Godds or Mullen, Nicola Mullen or something. I don't know her. She's a Canadian. Natalie Mullen, yes, in her master's thesis. It's a pretty heavy master's thesis, but it's very good. And we've been looking at those as well. There are some of the references. The VE, and that's the Sprower and Van Eyl. There's some stuff in there, obviously. This is the Hamming codes one here that we've submitted. This has been waiting to appear for about 6 months. It was online first very quickly, but so this is the first paper with these RLCD things. And now this is the PyZ ones, which is work in progress. This is Giraffe's PhD thesis from 2005. Massey, and I think you saw the other 2 down here, Mullen and PyZ. So I guess that's about finished.